So we'll continue with our discussion of the depth first search. We'll try to see how it works, how it behaves. We'll continue our discussion over which soon after we'll start off with what is intended to be done, the intelligent search, the heuristic techniques or the ASR algorithm. So we were there at the depth first search. Vertices, edges, the source and the goal. What we simply said was that for every vertex, let's say X, we simply said that color was simply traced out to be white. We said that the distance would be X, would be some infinity. The parent, of course, would be the parent of it was initialized to be null, and this way we initialize it and we try to find it out what would be the connectivity. Now that algorithm, what was written, it's basically intended to find out the goal inside the entire graph. So basically we did not start it from the source, but what that time we did was that we simply said for every vertex, now I'm not specifying that it starts up from the source over here, so there's no source. I simply search for this goal node. So I say for every vertex X in graph, the time was initialized to be 0 over here, and I simply said that you please visit it. And that's how I finally computed the entire DFS tree, where each and every node was tried to analyze and was trying to find out. And in the same algorithm that we wrote, there was a DFS visit. What it simply said was the color was first initialized to be gray. The time was updated, so I simply said time will get increased. Every time I visit something, I will increase because I am trying to locate at the timestamp when this node is being processed. So right now this node is being processed, so I will simply say that I recorded the timestamp over here, that is D. I will simply say for all vertices y in expansion of V, if color is white, I'll need in the parent information that's only to trace it, to trace the kind of structure in which this vertex was found. So I simply say that parent of y, that's what I did not mention the previous time. The color, the parent will be taken out over here. I know that y comes from X over here. That's what I've updated. I visited over here. With y, and finally the color can be changed. That's what more or less what I wrote down the previous time. Except the parent information was not there. Now what is interesting thing about this search is that what we are trying to do is that we are taking into account disconnected graphs. We try to take into account the disconnected graphs, and how do we do that? It is after a search, the entire DFS procedure is exhausted, because this function would call this function and then this would get recursively called itself, and that is how my depth first search tree, it will try to expand, it will try to go inside, more inside from here, inside from here. It will try to go inside and inside and inside. It will try to go inside in a depth first manner. So first this entire effect could not find out anything, then it will try to trace back. It will try to be deep inside like this, it will try to deep inside like this, it cannot find something, it will deep back a little more. So it will cover up more or less this entire tree. But if I have got another subgraph over here, that's completely unconnected. What happens at the end of this procedure, all these nodes are black and all these nodes are white. At the end of this entire procedure, all these nodes are black, all these nodes are white, and therefore I try to find out whether it is possible to get into any vertex over here. And then the search continues. So it tries to go inside, and finally goes back. And towards the end, they all become black. So that's what I'm basically trying to do, is that over here I'm trying to find out new white nodes, and I'm trying to, over here I'm trying to go inside, and towards the end I can get my solution. Now we presented kind of two vis-a-vis concepts. The first was breadth and the other was depth. Breadth was when we were trying to expand horizontally in an iterative manner. Depth is where we went deep inside in a recursive manner. So what is basically the trade-offs between the two? That will be a little bit of our concern. So we'll look a little bit over these two things. What's the analogy behind these things? Now I know if my graph is highly connected, from any way I keep on walking, I try to take up a random search, I try to go deep inside, and I know that somehow I can get into the depth. That is when probably depth first search finds its application. I'm not interested in getting out the shortest path, I'm just interested in seeing whether the goal can be reached or not. I go from a node and I keep on traveling in any manner, favoring the depth. The breadth will give me one very good thing. It will try to give me the shortest path. It will try to give me the shortest path from the source to the goal. And that is where you expand horizontally. So basically in any graph, if I look at only the current nodes, you've got two interesting concepts. From any node, let's say this was a source, are you interested in going vertically deep inside? This will be done by the depth. Or are you interested in moving horizontally? Now you have no idea how deep the goal is. You have no idea how deep the goal is. If the goal is very deep and by chance you choose a breadth first, if the goal is very deep, quite connected, and you use breadth first, it will have to process all these nodes until it reaches the depth. But that may, on the contrary, pick up the right nodes and push up into the correct architecture and reach. But on the other hand, if the node is on shallow, depth first will be taken a wrong way and it will go completely wrong, whereas your breadth first search will quickly search in a breadth first manner and it will get. So whether we have to exploit the breadth or the depth is an issue that is dependent upon the problem and cannot be guessed. And again, both have got different time complexities, they both have got different space complexities, considering the fact that it is unknown what would be the location of the goal. In both the cases, of course, the worst time complexity will be when the entire graph is expanded, when all the nodes are processed. That will be the worst case of both of them. The time complexity will be exactly the same. So this dependence of not knowing the problem puts a heavy constraint on us that we cannot decide whether to go for breadth first or to go in for depth first, and that is what again the advantage of one would take over the advantage of the other, and that is why we are completely undecided whether in a problem breadth first should be preferred or depth first should be preferred if we have no idea regarding the problem. Of course, if you have an idea regarding the connectivity and all, you can probably do something. The other algorithm that I will not touch upon is the iterative deepening algorithm. Again, an interesting combination where breadth first and depth first are used. The iterative deepening is essentially a depth first search algorithm, but the maximum level in which your graph can expand, the maximum depth in which your algorithm can go, they are restricted. And as the algorithm proceeds, we keep on removing these restrictions to a higher level. So this iterative deepening search, what it will essentially do is that it will try to remove one limitation of the depth first, and that is going indefinitely inside in search of the depth. This is what iterative deepening would essentially try to remove out as an algorithm. And again, you restrict the level you restrict the depth to some level, let the graph search for it. Later on, leaves that level. If the node is still not found, you leaves it up more. That's how the entire algorithm proceeds. We will not be touching upon this algorithm right now. We will directly come into some kind of intelligent techniques in graphs. We will try to find out into some kind of intelligence, and that will be the phenomena of heuristics. What if I have a graph? Let's say this was the graph, this was the goal, and this was the source. What if I have some kind of graph that is only available to me? I have some idea in how every node is close to the goal, and that is known as the heuristics of the goal. So I'd say heuristics of any vertex V is approximately the estimated distance to goal. That's what happens. My heuristics are the estimated distance that it takes to reach out a goal. Now, the intelligence is in how this heuristics is defined. The entire intelligence is in how this heuristics is defined. That is, when given any node, can I try to find out what would be its distance from the goal. Now, in some cases, of course, it can be defined. In some cases, it would be possible for us to define this heuristics. That is where these heuristic search techniques are used. Now, consider the problem of maze solving. We have a maze. Let me say these points were not allowed, these are not allowed, these are not allowed. And let me say there is again a blockage over here and a blockage over here. I need to find out a path from source to goal, which clearly these two. I can say approximately, if I can of course convert it into a graph where each cell is a vertex and these are the edges. So I'll get a nice little graph over here representing all these. This would get again expanded out over here. So this is how I will basically convert this into a graph, and over which I can use a graph searching technique. There will be some points over here and so on. Now any vertex V over here has an x coordinate and y coordinate. Let me take this as the axis system. It has an x coordinate and y coordinate. The goal again has a gx and a gy. A source of course has an sx and an sy. That's its distance. I can say the heuristic cost of any vertex V, that is at location x comma y, is nothing but the distance from source to goal. It is the distance from source to goal. So I say either V minus G, or I simply say the norm between xy and gxgy. For most of the cases, this would come out, we'll either take a Manhattan norm or we'll take a Euclidean norm. Let me take up this as the physical distances, the Euclidean norm. So we basically assign some kind of heuristics to this. We said that if you are at any vertex V, as a problem, we give you some kind of technique, we give you a function by which you can come to know approximately how close are you with the goal. Now one thing very important is that it tells you approximately how how near you are from the goal, because you have just made a guess over here. You just made an intelligent guess over here. It may be true, it may not be true. Now consider the same problem. You consider this problem. If I take in a vertex over here, its heuristic distance would be, let me say 1, 2 and 3 and 1, 2 and 3. That will be 3 square plus 3 square. So this distance would be come out to be root of 9. This would represent this distance. Now we've said that you are at the distance of root 9 from the goal. That more or less means that by equivalent number of steps you can reach the goal, but the truth is not this, because there is a blockage over here. The actual distance that the system would take, the actual distances are much larger than that. So this is a point where the heuristics does not work at all, because of a blockage. Because of a blockage in between. The heuristic value computer is wrong. But if I do it for here, it tells me exactly the location that separates. That's true. It is telling me exactly, the heuristic is giving me precisely the correct number. So since heuristic is a guess, the guess can be correct, it can be underestimated or it can be overestimated. Sometimes it may even happen in problems that you get a very large heuristic value, the actual value is to reach is much less. So heuristic is what we apply completely as a guess. And secondly, to all these vertices over here, I can have some heuristic equals to it. For all these vertices over here, using some technique, I can calculate a heuristic value to it. So now the entire problem of working with heuristic search algorithms is if I can frame this heuristic value in some mechanism. For some problem it's very simple, for some problem it's not so simple, you have to make it some intelligent modeling. And again, if I'm able to do that, it's always better to use this search rather than any other search. It will always be better to use this kind of algorithm. The next one I discuss is the A star algorithm. Again, this is a graph search algorithm. So we've got a source, we've got a goal, we've got all these vertices A, B, C, D, E, F, G, H, I. You've got all these vertices. In place of colors, I take something very close to it. In place of storing the information about whether the node has been processed, whether the node has been seen, not processed, or whether the node has not been processed at all. In place of that, in place of storing them inside the vertices, let me store outside the vertices. So I make in two lists. One is called as the open list, and the other is called as the closed list. Let me make two lists over here. These stores all the black nodes, this stores all the grey nodes, and everything is the same. Every node over here will have three types of costs. Every node over here will have three types of costs. One that I have already mentioned, that is known as the heuristic cost. That's exactly what has been mentioned over here. The other one is known as the historic cost. This is exactly the same that used to be when we discussed the distance parameter in the breadth first search. This is exactly the same cost. Now since it is exactly the same cost, that is computed out to be a cost that returns you the distance from the source. It returns you the distance from the source. Of course, when we talk about the A-star algorithm specifically, it is unlike the breadth-first search where it gives you the least cost from the source to the goal, but it does gives you a cost from the source to the goal, from the source to this vertex V. And the other thing that we would be taking is the total cost, which is nothing but a summation of both these costs, the heuristic term as well as the historic term. Let me make a Gx Gv plus Hv. This is precisely known and this is a guess. This has been what we have been guessed and this is what precisely was computed as the distance from the source. So we proceed exactly similar as we did in the breadth-first search. We proceed exactly in the same manner. Everything in this mechanism would remain the same. We'll go on expanding the graph. We'll go on taking some root from the graph, and meanwhile we'll go on finding out these values. Now, since I assume that it's an A-star algorithm, let me very simply let me assign any random values to each one of these nodes. The goal will have is precisely at the goal, so it will have a heuristic value of 0. And let me say this was 5. Let me make it 7. Let me make it 10. Let me make it 5 again. Let me make it 12. Let me make it this 13. Let me make it 18. Let me make this 20. So these are some random heuristic values. We've already assumed that there's some function exists that returns you heuristic value. So if I say h of b, there's a function that will return 18. This we have already assumed. And now the example of assumption is this problem. So h is the heuristic cost, g is the historic cost, f is the total cost. So first let me start off with the source over here. Initially all the historic costs are assumed to be infinity. That is what happened when we talk about the breadth-first search, where these things were being stored inside the vertex. Here nothing is being stored inside the vertex, they are being stored in this kind of list. So we'll write down the cost as we go about expanding the graph. As we go about, we'll keep on writing these costs down. So initially, only one node we place the source, that is the node A in the open list. This has a heuristic cost of historic cost of 0, a heuristic cost of 20, and that means a total cost of 20. This is the total cost of A. At any stage of time, when we were discussing the breadth-first and the depth-first search, we had a couple of gray nodes that were nodes that were seen and not persist, and the intention was to take out the gray node and turn it into a black node and expand the other node. So the nodes expanded, they became kind of whenever we took out the node, it became black. Whenever we took it out and when it was already processed, it was already expanded, and the new nodes were again added up in this open list. In breadth-first, what we were doing is that this open list was a queue architecture. In breadth-first, it was a stack architecture. Here, this is basically a priority queue, where the total cost, or FV, this decides the priority of processing. At any time from this list, we extract out the cost that is minimal. We'll try to extract out the minimal cost in this entire list. So basically, if I go with A is already expanded, that means it is cut from here, it is put up in this node. When it was put up, it has a cost of 0 plus 20, that is 20. I get B and C. So I insert it over here, B. Now while I am inserting it over here, I'll have to write down the cost. The historic cost will be 1. The historic cost of source was 0. So the historic cost of B would be the historic cost of S plus 1. The heuristic cost I have already assigned as 18, so this makes a total cost of 90, and C, that had a historic cost again of 1, a heuristic cost of 5, that makes a total cost of 6. These are the two insertions that I have done. Just in case my graph was weighted, there was a weight over here, there was a weight over here, there was a weight of here, there was a weight of here. The historic cost of this would have been the historic cost of this node S over here plus this weight. The historic cost of C would have been the historic cost of A over here plus this weight. So it does not matter whether you are into a weighted graph or an unweighted graph, the algorithm would work the same. If you are in a weighted graph, it will increment by the weights. If you are in an unweighted graph, the weights are 0 to 1, it will increase by factors of 1 that I mentioned over here. So now I will process from this queue C that has the lowest mode priority. I will process this because the priority is lowest here. So I will again take out C. I will see out over here, which had a cost of 6, 1 plus 5. So C is gone now. I get E and F. E has a historic cost of C plus 1. So the historic cost of C was 1. So the cost will be 1 plus 1, that is 2. And the heuristic cost I have already assigned to be 10. So this gets 12. And F, this is E. This had a historic cost of 7. So that would make it 9. And F had a historic cost of 2. That is equal to historic cost of this node C over here plus 1. So this has a historic cost of 1. So this will have a historic cost of 1 plus 1, that is 2. And a heuristic cost of 10, that will make it 12. And similarly, now there are 3 nodes. Priority 19, priority 9 and priority 12. So priority 9 is lowest. Priority 9 is lowest. So I take out E. I take it to this out, I get H and I get I. I get H and I get I. So H is inserted and I is inserted. H, the historic cost will be the node that I have taken out that has a historic cost of 2, so it will be 2 plus 1, that is 3. And 5 has already been assigned as the priority value, so it gets 8. And I, the historic cost will again be 3, that is the historic cost of E, that is 2 plus 1, that is 3, plus the heuristic cost, that is 0. And of course, in next step, I extract out I, and that is the goal, so my goal is found. That's how I proceed out with this. Exactly the same fundamental. As the breadth first search, exactly the same thing, except for a queue, I have replaced it with a priority queue where the priorities are the total values. Where the priorities are the total values, that is the total cost. So just a little bit of explanation on what A-star algorithm is trying to do out over here. A-star algorithm is trying to process nodes that are likely to have lowest total cost. The total cost of any node over here, represents the estimated total cost from the source to the destination. So at any node which has a total cost assigned to it, it is the estimate that we have made in its distance from source to goal. And of course, this estimate can be broken down into 2 parts, a known estimate and an unknown estimate. The known estimate, the historic value, and the unknown estimate, the heuristic value. And I call it estimate, that means there is some uncertainty that's only there in the historic value, it's not there at that's only there at the heuristic value, that's not there at the historic value. So So what we are trying to find out at every interval of time, we are trying to find out the lowest total cost nodes. Now this entire problem is like there is a graph that has been given to it, that we have been given. I am aware of some list of nodes, that is the open nodes. I go to any node, I see what is the total cost of that node, and then I go further. I try to go using a route that according to me, according to the estimates given, have the lowest total cost. At every point of time, I try to go about with nodes having the lowest total cost. So that is what happens in the open list. That is what happens with this list. As I go further, as I go on processing, the nodes that have already been processed are put into the closed nodes. Now there are some small invariants that sometimes we would like to consider. There would be an invariant that will say that let the total cost Fv be nothing but Gv plus alpha times Hv. Here alpha is known as the heuristic contribution. And of course this thing you can sometimes even be written by 1 minus alpha Gv plus alpha Hv, where we assume that Gv and Hv are already into the range of 0 to 1. So alpha contributes which what would be the contribution of each factor. So based on that invariance, but the important point here is that we try to have a heuristic contribution to this. Now there is another thing important. If I take the cost only to be Gv, I do not consider the Hv parameter at all. So all the heuristic costs would not be considered, and I say that the total cost is nothing but Gv. So basically I process my open list only according to Gv. I process my open list only as per the Gv values. So that would happen if I do this thing. I am on a path, I keep on visiting nodes, and whichever nodes I go, I select the node that is the least distance from the source. I go on expanding in this manner. I go to a node, at any time I process a node that is at the least, from the least distance from the source. So what I am eventually doing is that I am making this algorithm exactly equal to the breadth first search. This algorithm will be exactly the breadth first search in a weighted graph, in an unweighted graph. If it's a weighted graph, it would be the closest possible weighted substitution to the breadth first search, where according to the weights, it will have a level by level. It will have a level by level what we saw deepening strategy. Of course, here level would be based on the cost. The lowest distance from the nodes first and the largest distance from the source again. If we do this thing, we are doing one thing. If we are not considering the heuristic cost at all, we are trying to be very safe that heuristics will not be able to misguide the system. That's why we go step by step. We exactly go step by step in which one node, after that we follow the other node, and after that we follow the other node, trying to complete as much breadth as possible. If we do not consider Gv, we only consider Hv. The first thing that I introduced was if V is nothing but Gv, this became a breadth first search. If I say if V equals to Hv, this is known as the heuristic search, sometimes also known as the best first search, the best heuristic value first search. Here what would happen is that the historic parameter is lost. The historic parameter is all gone. So at every step I am not trying to minimize the total cost, I am trying to find out new places that are probably much closer to the goal. At every point that I go about in my open list, I have a series of options available. I have to pick one of them. I pick up the one that is likely to be closest from the goal. That is likely to closest to the goal, and I pick up these values. I keep on moving in this manner. So there are basically three invariants. The ASA algorithm that try to optimize the total cost from source to goal. The selection of nodes from the open list was such that the total cost is minimized. The breadth first search where the smallest distance from the goal was optimized, and the heuristic search which kind of tried to go about places which had the shortest distance from the goal. Now by controlling this parameter alpha, we are trying to make a search algorithm that will be a bit biased. That will be breadth first search biased to some degree, and that degree is denoted by alpha. If you keep it 0, it's entirely breadth first search. If you keep it something that will over-dominate the parameter GB, it will become entirely heuristic cost, and all other cases intermediate. So that's a breadth first search biased to some degree by the parameter alpha. So in the same graph, if I had to use a heuristic search, I would have taken the open list, closed list, take S heuristic value of 20, extract it out, put it up in the closed list, take B heuristic value of 18 and C heuristic value of 5, take out C heuristic value of 5, I get E with a heuristic value of 7 and F with a heuristic value of 10. I take out E with a heuristic value of 7. I get H with a heuristic value of 5 and I with a heuristic value of 0. I take out I with a heuristic value of 0, and that's what I get my final answer. So similar thing. I'm not taking the sum, I'm taking only the value of, I'm only the heuristic values. This exactly the same as my A-star algorithm behaved. So again, more or less writing down the algorithm is exactly similar as the breadth first search, except for this one parameter that these two separate lists are provided. Except for that, we have got maintained two separate lists over here. So basically an A-star algorithm with some source and some goal. What it would basically try to do is that it would start off with some kind of initialization. So my closed list is initialized with null, my open list is initialized with the source. The source already has a heuristic value calculated. So basically I get the heuristic value of source is known as per my heuristic function. So I say it's simply the heuristic that will be returned. My historic cost of source is known to be 0. I simply say that the total cost of S is HS plus GS. I take an open list, I enqueue source over here with priority Fs, and then my simple loop starts. I just say while Q is not empty. Similarly, simply find out, take out the value with the lowest priority there. So I say dq from this q, I get a vertex v. I'm having a priority based dq operation where the lowest priority would be dq'd over here. I simply say for all vertices in expansion of v, let me say for all vertices x that are there into the expansion of v. Now there would be a couple of cases over here that were not prevalent into the A-star algorithm. If x is neither in open nor in closed, I can simply process it. I can simply process the node x. So all I say is that the heuristic cost of x is given by my heuristic function. the historic cost G would be given by the historic cost of the parent V plus weight of x to V in case of weighted graph, else I'll just assume 1. The priority fx can be calculated. Once I got my priority x calculated, all I'll simply do is that I'll NQ x with priority fx, and that's all. Towards the end I simply terminate. I'll check it for the goal. I'll check it if V is goal, then return V, and of course towards the end I'll simply return null. By chance if the goal was not found, I'll simply return null over here. Now one thing you will need to ensure that because heuristics have come into play, I can always revisit a node if its heuristic value improves. Or rather I should say the total value improves. The heuristic value is constant, it does not change with time because my heuristic function is constant over all the nodes. So whenever the same node is given to produce the same heuristic estimate to it, but my total cost can change. I can go about a node, I can revisit a node, and if its total cost happens to be changed, I need to update the total cost. If it's an open node, I only need to update the cost. So I basically say if x is in open, I'll just update cost. And if x is in closed, I'll have to update the cost of x and all dependents. I'll have to update the cost of x and all dependents. Again, one thing that is not ideally taken out over here is the concept of parents. The parents would be, for source it would be phi. I'll update out the parents over here. At this line step I can also update the parents. I can take the parent of source to be null here, and that's all. So the only difference that lies here is that if a node is being revisited, I have to see whether its calls have improved or not. If its calls have improved, it has to be reflected. The similar algorithm will be for the heuristic search, except for that we try to keep on going in place of the best kind of graphs. Another small invariant is what we have introduced in one of our publications. We have an open list over here that at any point will have multiple entries. Let me say this is the total cost at any stage of time. And so on. I've kind of sorted it up because normally you have to do it if you're working with DSL algorithm. You have to find out the least priority and process it up. So that's why you need to sort it up. What we ideally did was we broke that into some alpha parts and we processed all these nodes parallelly. This was known as the multi-neuron heuristic search, something that comes up from one of our publications. What the motivation was, if the heuristics changes sharply. You visit one node, the heuristic is very good. Suddenly you find out that path is not possible, the heuristic changes sharply. For that we consider that always expanding out to the best node would not be a good solution. If heuristic changes sharply, you will have to backtrack the entire amount. If the heuristic changes sharply, then you have to backtrack the entire amount. So if I, in any trivial manner, if I would have processed this node, I would have processed this some later stage of time with the addition of this. What if this node was the one on whose expansion the graph had, and then is what we experimentally saw that this algorithm beats all the other algorithms in terms of execution time, and time was measured in terms of the number of nodes expanded. This had the least number of nodes that were expanded. So again, it's like all kind of tweaks that we happen in the open list. It's only the various algorithms, they only differ in how we differ in our expansion towards the open list. Again, an algorithm says that you take the best k nodes over here and you expand them up. So that's another invariant. So what do I do at any point of time? I see the open list, I find out the best k elements and I expand all of them parallelly. Expansion of this, expansion of this, expansion of this, expansion of this. So lots of interesting algorithms that you can make over this. All more or less lying on how you process the elements of the open list and what order you process, and of course if you change the heuristics, then that is again that how you take into heuristic contribution into role. Now we had, while migrating from bed first into this problem of ASA algorithm, we had made one strong point. We had said that the open list and the closed list would be maintained, and all these values would not be stored embedded into the graph. That was because of one thing, that whenever these algorithms apply, it may not be possible that you have a graph. It may not be possible that you have the complete graph available with you. So that is when the graph moves as a system of states. I'll take in a very short problem. I'll just try to solve a bit of it. Suppose there were two jugs. This has a volume of 4 liters and this has a volume of 3 liters. Now what happens is that I have to get 2 liters in either one of these jugs. That is what I am supposed to do. And of course there is infinite water that is available. Now how do we approach solving this problem? I say both these jugs together make it a system, and the system always has a state. So let me take a representation technique of this. I say volume of water in jug 1, volume of water in jug 2 is my system. Now this completely defines a system, and let me call this as a state. A state S1 can be transformed into a state S2 if I can have a unit operation that changes state 1 into state 2. If I can do some kind of unit operation that changes state 1 into state 2, I'll call it as S2 is reachable from S1. So basically what are the unit operations here? I can fill water in 3 liter flask, I can fill water in 4 liter flask, in 4 liter jug, I can drop water from 3 liter or from 4 liter, I can put 3 liter over 4 liter, I can put water from 4 liter over 3 liter. So it's like I drop in, I have jug 1 over here, jug 2 over here, I drop in water, or I fill these, or I exchange water between these. So let's, again, the various states in the system are not known. There will be numerous states. I have to just make sure I find out a state that says 2 and anything over here, or a state that says anything over here or 2. Now let's try to find it out. I'll only model it up as a graph, and rest the standard breadth first search technique is enough. I'll only model it up as a graph. Now of course breadth first search, what the algorithm that was written was not had this kind of initialization that will not be do. So in that case, resort to the ASA algorithm with the heuristic value 0. That would make a complete breadth first search that moves in states. So we start off with, let's say 0, 0, both jugs empty. I apply an operation that says fill in water at the 3-liter jug, this one. So my state becomes 30, or I apply an operation that fill in water in the 4-liter jug, my state becomes 04. These are two of the operations that I can probably do. I can fill in water at either of these tasks. If I drop water, then it will be in the same state. From null you get into null. If I put water, then again it will be null state. From 40 again I can go on into multiple phases. One of which is of course drop in water from the 4-liter. I'll get back into graph over here. Or I can fill in the 3-liter flask over here. From now on I will draw both the both pointed arrows. This is reachable from this, naturally this is reachable from this for this particular problem. I can go about with filling 4-liter would again be useless, so you will come up to 04. So I say drop 4-liter into 3-liter. 1-liter would overflow and my state would be 4 and 3 and 0, which is exactly as the state. So I connect it up like this. And so on, you try to expand the graph until you get to 0 or 02. So until you get 02 or 02, you try to adjust this graph, and the program would again be simple. If you are trying to write an algorithm for this, it would be very simple. All that you need to do out here is you enqueue a state known as 00 while queue is not empty. You simply dequeue a state x. If x is 20 or 02, you simply go about else expand x. In expansion, you will get a collection of states, let's say y, and again you check out whether y has been already expanded or not. So y contains in the closed list or not. This enqueue is basically an open list. You make it a closed list. If it is in the open list or the closed list, do nothing. Else, if it's not there in open list or the closed list, you simply enqueue y. And that's all. That's how you can go away. And somewhere in here, you will basically find when x reaches the goal, this is the state that you can return. So again, the problem was that the entire graph was not known. Now imagine if you are into a chess playing algorithm. Imagine if you are there as a chess playing algorithm. If you are making an search technique for a game like chess, where multiple moves are possible. Any condition of the board, which means that your first block was occupied by this person, second block was occupied by this thing, third block was occupied by this thing, maybe fourth was occupied by all. That is one state of your system. That is exactly one state. If you are dealing with such kind of problems, the number of states, they are massive. They are just massive. You imagine that each of these 64 blocks can be occupied by any one of the players or be empty. All this will result to different states and the multiplicity of the connections possible. If you are dealing with such kind of massive graphs, you cannot go about initializing the entire thing. That's how we've taken a state space approach. We keep on expanding the states and storing the states into a system. The only problem is that how do you represent this thing? And how you can represent your system state as an object over here, and that can be worked upon. In this problem, we somehow did not have the heuristics defined. It's very difficult to define the heuristics. If we would have got some kind of heuristics that would be possible to get in the other algorithms, then this would be replaced by the standard ASA algorithm where the heuristic picture cost would come into picture. Right now it's only based on the historic cost that we are trying to enqueue and dequeue. This thing would get based on some heuristic cost, and that is what makes in the entire system. That is what makes in the entire system that runs. we'll deal with some little bit of heuristics and working with that, and the main problem that we consider for the next session would be the clustering algorithms and the what is the fundamental, what is the use of clustering. That's what we would be dealing next.